Hi there, my name is Daniel Parks. I'm a final year PhD candidate studying environmental science with a focus on post-abrupt climate change. For this talk, we're going to be taking you through the carbon cycle with a focus on the oceans. I'm then going to talk to you about some of my work where I've been looking at ocean mud and using that to reconstruct past climates. So to kick off the talk, we're going to talk about the carbon cycle, take you through some key terminology, and then talk about this on several different timescales. And it should give you an idea of what the carbon cycle currently is and what we can look at in the past. I'm then going to talk to you about what we can do with ocean mud. And this is mud that we get from the bottom of the ocean, and we use this to reconstruct past climates, and it's what I do in my PhD. Further from that, I'm going to be talking to you about the importance of the global ocean conveyor belt, which transport heat throughout the northern and southern hemisphere, as well as nutrients. I'm then going to go on to talking about some of my research, which I'm hopefully describing as cutting edge, and trying to get you to have a feel for the importance of studying abrupt climate change. And then I'm going to go on to my journey on how I got to where I am, as you might be thinking about this yourself going into the future and whether or not you want to be a past climate researcher. So, let's look at the carbon cycle on a variety of different timescales. Before we get started, there's some key terminology that you may have come across before that's really important to keep in your head as we go through the talk. The start of what we're going to talk about is carbon stores. There are many different names for carbon stores. You may have come across the term carbon reservoir, carbon pool, carbon stock, carbon sink. This is all just where carbon is stored or where it exists. And you can think of this as like a forest where it undergoes photosynthesis, this stores carbon, or you can think of this as shells which use carbon to grow, or you can think of this as carbon burial in the deep ocean. There are several examples of places that store carbon simply by existing or by processing it. Then we go into carbon sources. And you can divide these into natural sources of carbon and also anthropogenic, so human-caused sources of carbon. And these are just where carbon is produced and is transferred to the atmosphere. A volcano is an example of a natural source of carbon, which is emitting a bunch of carbon dioxide into the atmosphere during its eruption. But you also have power plants through the burning of fossil fuels, such as natural gas, oil, and coal, which release carbon back into the atmosphere when it was previously stored in a carbon store. So keeping on the topic of carbon sinks and carbon stores, this is a diagram of the fast carbon cycle. What's not indicated here is bedrock, which is actually the largest carbon store that we have, but there isn't an exchange happening between bedrock and the rest of the carbon cycle, so it's a closed system, so it's not indicated here. The thing I want to take home from this diagram, is that the largest carbon store we have is the ocean. It's actually much bigger than the biosphere, the terrestrial biosphere, which is actually taking up very little CO2 compared to what the ocean is able to do. This is actually really important for the future on whether or not the ocean is going to act as a carbon sink or a carbon source. As we'll see in the next few slides, the ocean has played a really important role at moderating the effects of increasing emissions by drawing down emissions and keeping them in the deep ocean. If that were to change, this could have really important impacts for how we predict emission scenarios in the future. Staying on the topic of the ocean being a carbon sink and a carbon store, at the moment around 31% of carbon emitted is being absorbed by the ocean, and since the pre-industrial period, around 40% of carbon emitted has been absorbed by the ocean. And this has a really big impact on moderating the increase of greenhouse gases that we output. And to put that into context, in the pre-industrial period, CO2 levels were around 280 parts per million. At the moment, they're around 415 parts per million. And if you were to add an extra 40% on top of that, if the ocean weren't to have absorbed that, you'd be looking at closer to 460 and 470 parts per million. So it's clearly played a really big role in reducing the amount of greenhouse gases we have in the atmosphere. But carbon storage in the ocean actually causes its own problems too, and actually has an impact of more carbon in the ocean, makes it unable to store as much carbon in the future. This is because carbon does a few things. It increases ocean acidification, and the increase in ocean acidification means it dissolves carbon in a way that means that things like foraminifera, which use carbon to make their shells, can't then form. It also increases the temperature of the ocean, and the ability for the ocean actually to store carbon reduces at warmer temperatures. So this has a feedback mechanism, which means as we emit more carbon and the ocean stores more carbon, its ability to store carbon then reduces. And this is where we get to talking about whether or not the ocean is going to be a carbon source or a carbon sink, and the impact that has on future emission scenarios. So moving on from looking at purely the oceans, looking at the overall carbon cycle, we can see on a range of different timescales the changes in carbon emissions over time. On multi-annual scales, which you can see on the graph displayed at the moment, we're seeing the past few years of seasonal changes in the carbon cycle, which have a gradually increasing trend. Then looking at multi-decadal scales, we're seeing that since 1960, which is what the graph now is showing, we're seeing that this is a much steeper trend. And this, we can see those multi-annual changes, but what we're now seeing is this exponential increase in CO2 over time. And this is following what some people might call the Great Acceleration, where CO2 levels start to rapidly rise. So we've been talking about measured levels of CO2 when we're looking at annual changes, multi-annual changes, decadal changes. But what if we want to go back further? Well, we can use this by looking at things like ice core records or ocean mud records, and we can reconstruct CO2 levels over several hundred thousand and even millions and billions of years. The graph that's on there at the moment is showing you CO2 levels over the past several hundred thousand years. So you can't see the multi-annual trends that we were seeing before, where we see seasonal cycles, but this is showing us a climatic history. Where we're seeing higher CO2 levels, these generally correspond to warm periods. When we have lower CO2 levels, these correspond to ice ages. And this is what we call glacial and interglacial cycles. Glacial cycles typically refer to the expansion of ice sheets in the northern hemisphere, whilst interglacial cycles are like where we have today, where we have warm climatic conditions which are ideal for warm adapted species to flourish. You can see that there are several spikes of CO2 levels which correspond to those warm periods, but none of them are as high as the present CO2 spike which we have associated with today. And this just shows the unique nature of what we're emitting at the moment through anthropogenic sources of CO2 rather than natural cycles. So going back to the multi-annual graph that we were looking at before, this is showing seasonal changes in the carbon cycle. What you have is a repeated upward and downward trend, which corresponds to the winter/spring release of carbon and then a spring/summer decrease in carbon. The winter/spring release of carbon is related to organic matter decaying and then releasing carbon into the atmosphere, whilst the spring/summer decrease in carbon is related to photosynthesis using carbon and then storing it within the vegetation. Now, if we zoom out a little bit and we go back to 1960, you can see that it's not really a progressive increase, but quite a substantial increase over a short period of time. What we call the Great Acceleration in 1960 is where this started to happen extremely fast. And we know that 90% of the carbon output is related to human sources. The key causes of that include both deforestation and fossil fuel burning. And I'm highlighting these two in particular because the first one is reducing the carbon sink, whilst the second one is increasing the carbon source. And whilst you're reducing a carbon sink, so that's the Earth's ability to store carbon, and increasing the carbon source, which is the amount of output of carbon, you're going to have this ever exponential increase. And until you rectify that by increasing your carbon stores and reducing your carbon outputs, it's only ever going to increase at an accelerated rate. And that's what you can see on the graph on the right here. You can see those seasonal cycles, but you can see it's getting progressively faster. And then if we zoom out several 100,000 years, you lose the ability to see that seasonal signal. You can still see the current trend in anthropogenic emissions. But if we're looking at all of the past warm and cold periods, we're seeing that the warm periods correspond to highs in CO2, and the cold periods correspond to lows in CO2. And we know this because if we look at the fossil record, We can see that in past warm periods, places like London have had hippos in, and that requires temperatures to not go below freezing, but also places like London were perfectly suitable to have woolly mammoths. So we know that the Earth's climate has changed through past warm and cold periods over time. And we can get that in terms of temperature from mud from the ocean floor, from ice core records and the fossil record. But what we can also see from this graph is that the current levels of CO2 have not been seen at all over at least the last 800,000 years, and actually a lot further before that. And it's really striking that we can see this very short signal despite zooming out to several 100,000 years. So this takes us on to the next section of the talk. In the past few slides, I've been talking about how ocean mud can be used to reconstruct past climates. And for the next few slides, I'm going to be talking to you about how we collect ocean mud and what actual fossils we can use to reconstruct past climates and how we go about it. So what is ocean mud and what does it have in it? Well, ocean mud is just unliquefied sands, silts and clays, and it sits on the ocean floor. When we say unliquefied, we just mean it has not turned to stone. These can be several hundreds of meters thick. They're deposited by ocean currents which pass over the ocean floor and carry sediments which settle at the bottom of the ocean. As those sediments settle, they bury a variety of different information we can use to reconstruct past climates. Examples of this include fossils, sediments, and even rocks, all of which we can use to reconstruct the past. So the first of these I'm going to talk about are foraminifera. We talked about this in one of the first few slides. Foraminifera use carbon to create their shells, and this helps store carbon in the deep ocean. We can also use these to construct other things. So on the left we have a benthic foraminifera, and this just means a deep ocean dwelling foraminifera, and that helps record changes in the deep ocean. It can also help record changes in global ice volume. On the right we have a species of foraminifera which is a polar species, which means we can use the relative abundance of that to look at changes in sea surface temperatures or to positions of the polar front. The next thing to talk about is just rocks. So you have pebbles, rocks, sand-sized grains of things that under a microscope look like very large rocks. This is an example of quartz. And we can use the appearance of these to look at iceberg activity, and this can tell us about ice sheet activity. We also have proxies that we refer to as dinocysts. These can tell us about a variety of things, such as sea ice and the presence of it throughout the year. And then we also have diatoms, which can tell us about a whole different range of things in the ocean, such as nutrient availability, salinity, and we can also see these in freshwater systems and compare them. These also play an important role in the carbon cycle as they require carbon to grow. So how do you go and collect ocean mud? Well, the depth of the ocean is actually really variable. In some areas it's only several hundred meters deep, whilst in other areas it's several kilometers of meters deep. But to start off, you've got to go get on a boat. The top photo, which is shown here, is the original ODP cruise. And you can see that there is a rig on top, which looks similar to an oil rig, which would drop pipes down to the bottom of the ocean to collect mud. Underneath that is a far more up-to-date version used for the IODP cruise, and you can see labelled as where the coring rig is. What they do is they drop pipes down to the bottom of the ocean, which they repeatedly do to collect deeper and deeper sediments over time. And they actually collect more than 100 meters worth of sediment in different locations. And then they analyse these on the boat for a preliminary analysis. These end up stored in fridges in plastic pipes. It's organic matter, so it will go mouldy over time, so it needs to be stored somewhere cold. You can see on the right people working on these, presumably on the cruise, but also just an overview of one particular core and how you can see changes over time. Some of the changes, particularly climatic changes, you can actually visually see in the sediment. One example is where you have more calcium carbonate, sediment tends to be lighter. So we can look at the visual lightness score of the sediment. At some locations this responds to climatic cycles, so where we have higher amounts of calcium carbonate, we have warmer climates. And when we have lower amounts of calcium carbonate, we have cooler climates. This isn't true for everywhere, but it's just one of the examples of something you can get just by visually looking at the ocean sediment. So what do you do when you have collected the mud? Well, you generally order it from wherever it's being kept. This is because you've got to keep them in those fridges to stop them from going mouldy. Once you've got the mud, you can wash it through a sieve. This allows you to collect anything that's bigger than, let's say, a grain of sand, because most of the fossils that we might be interested in are larger than that. Everything else gets passed through the sieve and it goes into a large jar which collects the silts and clays. The fossils which are in the sieve, we then collect and identify them because this can tell us about changes in sea surface temperatures, it might tell us about nutrient availability, or other changes which may be important for looking at climate. For the silts and clays, the changes in size of the silts and clays might correspond to changes in the strength of the ocean current that deposited them. If you're confused, think about it like a river. When a river is stronger, it can carry boulders, large pebbles, rocks, whereas when it is weaker, usually an estuary, it can only carry those silts and clays. And during storm events, it can carry much larger material because it is stronger. The same is happening in the deep ocean. When the ocean currents are stronger, the size of the silts and clays that it can carry will be bigger on average. Whereas when it's weaker, this might be carrying smaller sizes on average. This sometimes corresponds to changes in the global ocean conveyor belts, or climates. And this is important for what we might look at in the next few slides. Now we can measure the size of those by putting them into a machine, and then it uses electrolytes in the water that we pop it into to measure 70,000 individual grains of silts and clays. It then spits out an average at us to tell us the average grain size. This is a photo of me doing that. It looks very, very sciencey, very, very technical. It's one of those very satisfying moments where you regularly get data, which is coming in every few minutes. So to summarize this, with the ocean mud, one of the most important things we can do is look at climate change in the past. We can do this because our deep ocean dwelling foraminifera, so our benthic foraminifera, using isotopic values that we can take from those, they broadly correspond to changes in global ice volume, which, if you think about ice, it melts when it gets warmer, it grows when it gets cooler, corresponds to climate change. We can also use this, in some part, to reconstruct the strength of the ocean conveyor belt, which is the next thing we're going to talk about. So, the ocean conveyor belt. The next few slides are going to give you a background to how this works, and then talk about why it is so important for our climate. So, there's some key terminology that you should really get in your head as we go through the next few slides, and keep that in mind, or refer back to if you get stuck. Thermohaline just means heat salts, and this is when we talk about thermohaline circulation. This relates to the global ocean heat and nutrient conveyor belt. When we talk about AMOC, this is referring to Atlantic meridional overturning circulation, and this is part of the thermohaline circulation, the global conveyor. This is the Atlantic part of the global conveyor belt. So, what is the global ocean conveyor belt, and how does it work? Well, it's density driven, and there's a few points I'm going to take you through to talk about what that means. To start off, warm water is less dense than cold water, and fresh water is less dense than salt water. And if you think of it in terms of just weight, if I had the weight of the water and I added the salt, it becomes heavier than just the weight of the water on its own. And that's what we mean by salt water being more dense than fresh water. The position of the conveyor is largely driven by deep ocean topography. So the conveyor belt moves along topographic highs in the bottom of deep ocean. The ocean conveyor starts when surface waters become denser and heavier and then sink. And this is generally because they become saltier. The causes of this could be evaporation or freezing of fresh water, anything which is taking fresh water out of the system, which is making the remaining water relatively salty. That sinking water then leaves a gap, and that has to be filled by more water. and that makes a conveyor belt. That water then sinks deeper and deeper like a river until it finds a layer which is a similar density itself, and then it spreads. If this is a bit confusing, there's something you can try at home. If you pour yourself a glass of cordial with some water and add an ice cube, as the ice melts, that fresh water will sit on top of the sugary water. In this case, the sugary water is similar to the salt water. Because the water has sugar and the water in as its weight, it is heavier, so that fresh water sits on top. But it is similar enough a density that if I mix it around, it all mixes together so that you can have a sugary drink. That fresh water then stays deep until it can escape, because the density is greater than that which is above it. An example of this is where you have wind blowing the surface of the water away, and if you remember, if the water is removed from the surface, something has to replace it. And if the density changes permit it, then that water can rise from the deep ocean and rise to the surface, or what we might call upwelling zones. If you're confused, think of it like an escalator. At the top step, it goes underneath and back down and new steps replacing it. As you get on, you're part of that conveyor belt and that step is moving further and further up, and as you get off the escalator, it returns underneath. Each step is being replaced by another step at the top of that escalator. Thermohaline works in a similar way, except with water. So if you think of where it is sinking as the top step, the particles of water move around the ocean until they get to that top step and then return. So now that we know that, why do we care about it? Well, sinking water transports carbon dioxide and nutrients to the deep ocean. And going back to talking about carbon storage, this plays a really big role in bringing carbon to the deep ocean and keeping it there. It also brings warm water to the northern latitudes, and there is suggestion to show that Europe would be 5 to 10 degrees cooler without this thermohaline conveyor belt. So this plays a really big role in providing nutrients to deep organisms, storing carbon which has been emitted into the atmosphere, and bringing warm temperatures to the northern latitudes. So now we're going to look at the AMOC, which is the Atlantic Meridional Overturning Circulation. This is the Atlantic part of the global thermohaline circulation. It transports heat from the tropical regions to the North Atlantic, polar and subpolar areas, which keeps us warm. But if we look through the Earth's climatic history, we have several examples where this has weakened, which has caused cooling in places like Europe. And we can see this from evidence in the ocean mud and the different information we can get from that. So what happens if it does weaken? Well, there is a very popular film about it, which you may or may not have watched. However, it's not quite dramatic as what happens in that film. But broadly speaking, this is based on a cooling event which occurred around 12 to 13,000 years ago, which we call the Younger Dryas. And this is related to an increase in fresh water which has been deposited in the North Atlantic through melting ice sheets, which has disrupted that density-driven ocean circulation. This causes cooling around the North Atlantic region, and in the graph on the bottom, this is just a measure of temperature. You can see that there's warming on the left, which is interrupted by this cooler period before the current warm period that we're in today. And the influx of fresh water into the system disrupts the haline parts of that thermohaline circulation, which then reduces the amount of warm water which has been brought to the northern latitudes. This is really topical and important. The film isn't new, but there are several studies, which are more and more of them coming out at the moment, as well as news articles that you can read, which talk about tipping points in the global ocean. And there are some studies and examples of this listed here. Most recently, we saw about the Gulf Stream collapse that we may see within this century. And you can have a look at some of these online if you wanted to read a bit more about them. But it is something that we're actively concerned about, the weakening of the AMOC, if not the collapse of the AMOC, and the impact that this will have on temperatures in the North Atlantic region. So, this brings us on to stuff that I've been working on. I'm going to give you a little bit of information on the research I do and what you might be interested in doing if you ever thought about going into looking at past climate change. So I look at an interval that we call MIS11. Now that bit's not really important, But what is important is you can see it on this CO2 parts per million graph here. It is a period which is around 420,000 years ago, and it was a warm period that lasted about 30,000 years. Why do we look at past warm periods? Well, MIS11, in that warm period, we see that we lose most of the Greenland ice sheet and the lower greenhouse gas levels that we have today. During MIS11, greenhouse gas levels were around 280 parts per million, which is similar to the pre-industrial period. But without those elevated levels of CO2, we see a really big loss of so much of the Greenland ice sheet. On the graph on the right, it shows the modern Greenland ice sheet, and then what was left of it in some modelled comparisons of the MIS11 ice sheet. You can see there's a small amount in southern Greenland and some in eastern Greenland. And we think this contributed several meters of sea level change to the global ocean. It's also really interesting to look at past warm periods because this particular one was 30,000 years. The current warm period has been about 11 or so thousand years long. So looking at something like past warm periods which have been longer allow us to see what happens to the Earth system over time if we have prolonged warm conditions. And in particular, looking at MIS11 allows us to look at the Earth system in response to a substantial Greenland ice sheet melt. Now we're concerned about substantial Greenland ice sheet melt because temperatures are high. They're much higher than in periods where we have seen a reduction in the Greenland ice sheet, which we have not yet experienced, and it is starting to accelerate. And when we talk about the 1.5 degree threshold, we're talking about when we start to see accelerated melt in Greenland. Now, why do we care about that? Well, I told you I look at abrupt climate change. In this talk, we've learnt that ocean circulation, it brings heat to the North Atlantic region, to the polar and subpolar North Atlantic. And without that, it would be much cooler in Europe than it presently is. We know that this is a density-driven thing, so it depends on the balance of freshwater versus saltwater. And we know that it has got weaker and shut down in the past. And we know in this particular warm period, MIS11, that Greenland melted quite a lot. So taking that all together, we know that the increase of freshwater from melting ice sheets has the ability to affect the global ocean conveyor belts in a way that may cause cooling in the northern hemisphere. And this is just an example on the right of a polar species increasing during a warm period substantially during a time we know there was melting of the Greenland ice sheets. And the wonder at the moment is whether or not these are related, and that's what I look into. So why should we care? Well, if we're looking at abrupt climate change, whilst on the long-term changes of climate, we're seeing this happen over thousands, tens of thousands of years. Abrupt climate change is the sort of thing that you start to see within a human lifetime. The impact of vegetation might be seen within 20 years or so, but the impacts of it might persist for hundreds or thousands of years. This particular event that I look at might have lasted for more than 1,000 years. And this is a long time, several generations, to have to be dealing with an abrupt shift in temperatures. The event that we look at is associated with a big change in vegetation across the whole of northwest Europe and in Britain, where we see this opening of the landscape, a shift from temperate to open grassland, or what we call glacial, cold adapted species. And this happens for a few hundred years. And this is because the ecosystems are fragile during these abrupt events. It also has the possibility of disrupting deep ocean communities and carbon cycling related to that. So this is something that we should be concerned about whether or not the Earth is approaching several tipping points. So I want to take you back to the fast carbon cycle diagram that we had at the beginning of this presentation. What we talked about then was the amount of carbon stored in the ocean, and how important that was, and how much bigger it is relative to other carbon stores. What I hope you can now take after this talk is how important it is at storing carbon, how its ability to retain carbon might be changed in the future, and also its importance in regulating the Earth's climate in short and long timescales. Now, if any of this really interested you, I've got a few tips on my journey into becoming a past climate researcher. So for many of you, you will be thinking about what you want to do next. And for some of you, you might be wanting to go to university. And for some of that lot, you may be wanting to study geography. And you may be really interested in this talk about how you become a past climate scientist. So this is just a bit of an overview of what I did. I did my undergraduate in physical geography, and that allowed me to explore current and past climate change, but I also got to look at social impacts of climate change and social geography more broadly. And this can be really interesting in exploring what you're interested in overall and finalising where your interests lie. I then went on to study quaternary science, which is looking at the past 2.5 million years of the Earth's climatic history. I went through different methods of how we reconstruct past climates and why that's important for today. And then that led me to doing a PhD in environmental science. This is a more broad title, but my title is specifically looking at abrupt climate change during MIS 11, which is that long warm period we talked about a few slides ago. And whilst mine isn't typical, I did all of my studies at Royal Holloway. The latest degree, the PhD, has actually also been done at UCL, so you can divide some of your time between multiple institutions once you go far enough, but at least for my undergraduate and postgraduate, I was based at Royal Holloway, which is in the picture on the slide. And during my first year of uni, I had the absolute privilege of living in this castle whilst I got to grips with university life. So, just some examples of things you can do whilst you're doing a degree in geography. The nature of it sends you on a lot of field work. During my time, I've gone to southern Spain, Sicily, the Scottish Islands, and this was all whilst I was at Royal Holloway. And these are because they're really great examples of places that you can see climate change. So in Spain, you can see the impacts of climate change on agriculture, but you can also see, because of changes in tectonics, climate change in the past in cliff faces. In Sicily, we can see Mount Etna, obviously, as one great example, but you can also again see the impact of climates in the Mediterranean. And in the Scottish Islands, we have great examples of climate change during the last glacial to interglacial transition, so the phase between the last cold and the current warm period. And on the image that we have there is several horizontal stripes that we see across the mountains, and these reflect positions of the height of lakes that were dammed there by ice sheets, and them eroding away the face of the mountain. And again, I did all of this at Royal Holloway. Now, I haven't done much field work since I became a PhD student, but you do have the opportunity to collaborate with people by going to conferences. So I've been to conferences in Norway and Italy, and soon to be San Francisco, but there are also conferences in the UK. And these are just great opportunities to network with researchers and finesse your interest. So that's the end of the talk. I hope what you've taken from this is the real importance that the ocean has in moderating the Earth's climate and moderating the carbon cycle.